Get started. Um, Hello, my name's Colin Choy. I'm the current Mark 11 Mechanical Technical Director. Um, this is a presentation on jig design for specifically our tabs that get welded onto the chassis. Um, just want to shout out Karo, our manufacturing chassis RE, who added a lot of these slides for standards on like design tips for making these jigs. So yeah, I guess we'll just hop into it. I guess like a bit of overview for today. We'll talk a bit about welding tab jigs. It's the shorter of the two presentations. And then after that, I'll go into a bit more on drawings. That's a little more in depth, going into a bit of GD&T. And then I'll do some examples of how to actually make some drawings on SolidWorks if you've never touched that before. But yeah. So yeah, these are just a reference to help you get started with jig design. In terms of timeline, we'll probably be doing jigs over the next 2 weeks before winter break. Um, get as many of them out of the way so they're already designed before we get back in winter. The chassis should arrive week one of winter quarter, which means we'll have to set it up in its own jig and then prepare all of our other tabs for welding. So, yeah, that's why we're doing this right now. You can always reference last year's jigs. They're all in the box for new members. Once you get access to that, you can view both Mark 11 CAD and then also once you get full access, you can also see like the Mark 10, Mark 9, and Mark 8 folders. So you can always look back at old designs. That goes for any sort of thing you're designing. You can always check the old stuff. And then if in terms of questions, you can always run your designs by me, your leads, or Karo, Josh, and Fana. Josh and Fana are the welding REs. So they'll be able to give you a lot more insight onto like welding accessibility and feedback. But yeah, I guess just getting started, like what is a jig? So whenever we refer to jigs, it can mean a lot of different things. It's mostly just like some sort of tooling that helps you either like station different parts in a certain orientation, whether it's for manufacturing, like you might have fixtures that you might call jigs for like when you're CNCing something, right? You might want to hold it in a specific orientation while you're cutting it. These jigs are obviously for getting our tabs welded to the chassis, so they're more like so yeah, they're welding jigs are pretty common. There's also assembly jigs, right? Things to like correctly align different components. So it's any bit of like tooling that'll hold your parts in a correct orientation. Um, and so, yeah, the jigs are mainly to constrain the tabs in their correct location. So that our welders can go in and be sure that it's in the correct spot as they just finish off the weld. They don't have to hold on to it or anything, keeping them safe. Um, and yeah, this is how we control all of the different like critical dimensions between tabs, how they're related to each other, and how they're like positioned on the global positioning like coordinate scheme. Um, so yeah, each tab, we'll talk about this a bit more for drawings as well, has like its own degrees of freedom, right? Or like directions it can move, how it can be rotated. So your whole goal is to completely constrain a part, right? Whether or not you're like bolting it in a certain way or having it like sit inside a pocket of like a 3D printed part, or something else that like ensures that it's fixed exactly how you like it. Um, this means like it's completely in your control. Jigs are meant to be like easily designed in an assembly. You need to be able to reference like both like the chassis itself and all the tabs on there, as well as the welding table that you'll see below. So over the next week, as all the tabs get finalized, you'll start to see more of the chassis jig assembly, which includes just the chassis, all the welded components that go onto it, and then the table itself, so people can start making their own assemblies with jigs in them. Um, and yeah, um, jigs are also a good opportunity to get used to working with a bunch of different materials. It's generally like a mix of wood, aluminum, and 3D printed parts. Um, so yeah, jump into it. So there's two main different types of fixtures that we'll be using for all of our tabs on our chassis. There's what we'll call jigging off of the weld table and jigging off of the chassis. And when you're looking at like when you're trying to design something, they both have very different like workflows. So it's pretty important to know which one you're trying to use beforehand. So starting off with jigging off the weld table, this is really useful. We'll use it for a lot of the suspension tab jigs, and it sort of constrains your absolute positions a little bit more. So you can see this jig is actually like bolted into the table, and that's where all of its components are connected to. It's not actually touching the chassis in any way, versus when you're jigging off the chassis, we're clamping on tubes and directly referencing them. So something you might realize, so like let's say I'm trying to constrain, these are for the A arms of the suspension. I'm trying to position all four of my wheels in a correct spot with as little like error as possible. But when I get my chassis on the table, you'll realize that there's still some error within your chassis, right? Like maybe it's too skinny in a certain region, maybe it's too wide, tubes are out of position. And if you're directly referencing off of tubes, your overall position might be off compared to like what you designed for in CAD. Um, so this sort of gets that out of the way where you're not actually referencing the chassis. You're just using like your global coordinate scheme. It's all off of the table, which is like known positions and stuff like that. So you're able to hit like tighter tolerances using some of like this Build Pro gear, which is like off the shelf fixturing items. Um, and like I said, it reduces some of the uncertainties that build up from the welded chassis itself. Some of the cons are because the chassis is not being directly referenced, this might lead to more tabs needing to be bridged or trimmed, since like the chassis might actually be closer to the tab or farther away than expected. So you might have a little bit of a gap that you need to bridge with like welds. Or you might need to cut down the tab if it's like running into it. So you're also limited more by hardware since we're using a lot of these tabling components. We have to be strategic about like what order we're welding all the tabs in, and this is the main like constraint for our timeline. Jigging off the chassis is really useful if you have certain components that are more worried about like relative fitment to the chassis. A good example of this is both our DI, our driver interface tabs, as well as our aero package. So for the nose cone specifically, it's pretty important how the nose cone fits around the front of the chassis, right? Like in certain areas, it hugs it pretty tightly. So if you use like the jigging off the weld table idea, your tab might actually be like pretty far off from where you wanted it, and now like there's a big gap in your body work where now it's affecting your airflow, stuff like that. So in those cases where it's more like about local accuracy, you can jig directly off the chassis and be pretty confident that like you won't have as many like gaps or whatnot. Um, but you might have a little like less what's it called accuracy in terms of tolerance, especially from between tabs between one another, if you're trying to maintain certain dimensions. Um, so yeah, each of these we'll talk about a bit different strategies you can use to improve the accuracy and stuff like that. So this is the Build Pro gear that was mentioned. We have a bunch of different like brackets, bolts, and risers that can sort of constrain your components. If you look at the chassis jig assembly, you'll see this later down the line, especially in winter. The chassis is like mounted on a lot of these different risers that are like constraining it in different ways, reducing all of its like degrees of freedom, as we said. So it's not able to rotate. It's not able to like translate anywhere in any direction. And you can slightly adjust these like they're all like threaded. So you can adjust these and measure different points until you're pretty happy with where it's like situated. Um, and yeah. So this is standard hardware that you can use, especially if you're doing jigging off of the table. All of these parts are within our box files, so you can find this in the chassis folders if you end up jigging with those. Um, and then one of the first materials like you'll be able to use is aluminum or any sheet metal. We'll generally use a water jet to obtain these parts. Water jetting, if you don't know, basically shoots like a high velocity stream of water with different like little like roughing materials inside. Like oftentimes it's like granite or some sort of sand in there, that some sort of abrasive that'll actually cut through any material. So this is really good for getting 2D profiles cut out of metal like really quickly, really easily. Um, we have a couple on campus and a couple sponsors who will help us procure all these parts. Obviously, the big like constraint of this is that it has to be 2D profiles, right? It's just a machine that'll shoot the spray of water in whatever profile you program it to, but they can't really angle or do complex like 3D geometries. So keep that in mind when you're like designing parts that are meant to be made out of metal. So this one, for example, this whole profile with all its like vertical holes were water jetted, but there's holes in another like in a different plane. We had to drill those ourselves because obviously the water jet can't do that. So that adds like extra manufacturing steps. That's just a bit of an example of like keeping in mind the limits of whatever tool you're using to make your parts. When you're making parts that need to be water jet, we also downsize any holes um, around to like 85% of the nominal diameter. Um, when it's spraying water, it goes at a bit of a taper to hit at a certain point. But obviously, once it goes past that point, you have a bit of a cone area. So this by reducing the diameter a bit, you reduce the chance that your hole will end up becoming oversized and like having a loose fit on your bolts. So just adjust all your hole sizes ahead of time, and then we'll just drill them all out when they get here. Um, but yeah, so that's for aluminum. Um, General advice for jigging off of the chassis. There's a bunch of ways you can do it, especially with like 3D printing at your disposal. And we'll also use like laser cutting wood if we don't want to use more metal, which might be more costly in terms of stock, since we have the maker space can provide us with like free wood and stuff. Um, it's pretty good for like easily getting like a bunch of versions out. You can quickly iterate through it since we can just do it in the makerspace. Um, some things to keep in mind, like this is an example design where you'll use these clamps or shaft collars, sort of. These will be 3D printed and they'll attach locally to any tube, right? So this is again like referencing off of nearby tubes rather than the table itself. Um, and then those guys will attach to a wood plate where you actually bolt your tab onto in order to constrain it. Um, so yeah, this is how you would fully constrain your jig. Um, I'll talk about a couple of like the welding considerations that make this design a bit better, and why you might like choose wood in certain areas versus 3D prints and whatnot. Um, for our non-critical tab jig materials, like you just saw, we can use a lot of wood and 3D prints. For wood, your main constraint, I mean, we can buy other kinds of wood, but your main thing is you'll be using 3/16 inch thick wood. This is just the given makerspace thickness. Um, some things to keep in mind though with wood, you might have some compliance issues, especially if you're making a very large plate. For example, the firewall spans the entire width of the car and has multiple tabs. If you tried making a plate that like spans that entire area, you might run into like warping issues where like the wood might be able to bend and whatnot. If any loads applied to it. So the shorter or the smaller size boards you use, the more stiff it'll be, less susceptible to compliance. But obviously, it's like a lot less stiff than if you were to use any sort of metal. So keep that in mind if you're using that. Um, with 3D prints, it's pretty useful to quickly get CAD going for any off the chassis mounts because you can use the cavity feature, which essentially in an assembly, if you have two parts overlapping, you can just make it have a hole like wherever they overlap. So you would just CAD this as a block that interferes with the chassis, and then just say cut out any material where the chassis would run through, and now you have something that just fits around the shape. So that's a pretty easy way to design that. Like you could probably make this in a nice 5 minutes, and then add your wood piece, and now you can actually weld your tabs on there. Um, yeah. I guess some other stuff with 3D printing, it's important to recognize like what orientation you're actually using for your print vector. So, um, one thing is if the printer, right, when it's laying down filament, it's very accurate in like it's like 2D plane, right, when it's just drawing out outlines, especially when you're making circular shapes and whatnot. But when it's stacking layers, right, there's a certain amount of like resolution you might run into with different print bed sizes, or sorry, uh print layer thicknesses. Um, so you might see that if you have a hole that you're printing vertically, it might end up like really ovular, or you might see like the layers are messing with its circularity. So if you're really worried about the fitments of your bolts and whatnot, again, you can do a similar thing that we do for water jetting, where you end up drilling out the holes afterwards, and you undersize it a tiny bit, um, or you just change your print vector. So any like the most critical holes you want to use are actually like facing or they're in like the 2D plane of your print bed. For jigging resources, again, like we'll make a chassis file once all of the tabs are in that just contains the chassis and the tabs in all of their locations. This is so like when you're actually making your assemblies, you don't have to keep loading every subteam's top assembly, which would be very taxing on your computers. So we'll just make a separate file that just isolates the chassis and all the tabs, and then put it relative to the weld table. This way, teams can actually put in all their jigs and see which ones like will interfere with each other, which will dictate like the order in which we need to weld tabs, um, or if like suspension is using some of like the Build Pro off-the-shelf hardware, um, can they weld at the same time as drivetrain, who might also be using some of those blocks? So that'll help us set the schedule for early winter quarter. Um, but yeah, as always, if you have questions, you can ask me or ask Karo, especially if you're looking at jigs. He'll be doing a lot more test prints and stuff for those collars that can be used for all of the off the chassis jigs. Um, yeah, so some overall like design considerations. This is more general and it's more applicable to like stuff outside of racing. When you're doing stuff like jigs, a big thing is tolerance and accuracy, and tolerance stackups you might hear. So with every part, right, like you might design it a certain way with a nominal dimension that you'd ideally like it to be at, right? If I say something's a quarter inch, hopefully it's actually a quarter inch. But as you start to get like need more and more accurate parts, you might see like once you go down to the thousandth scale, you're actually like a little bit off with every part. And this is just inherent, like nothing's perfect, right? No manufacturing system is perfect. You're going to have some errors whenever you make stuff. Um, some things like water jetted parts will have these rough edges, right? Which obviously like mess with that surface. It just is up to you whether or not you care, right? Like these faces don't actually interface with anything, so it's not really too much of an issue. But across larger assemblies, right, you might have certain dimensions that are pretty critical, but once you start to look at how many parts go in between, take for example the track width of the car, which measures the center point of the wheels on the left side and measures to the center point of the wheels on the right side or left and right side. Yeah, across the width of the car, which is a pretty simple dimension and is pretty like critical for like all of our calculations. Some of them are for like rules requirements. We can't go below certain uh, like lengths and stuff. But once you start to look at the actual assembly, you'll realize how many parts are in series, like just stacking one on top of another, right? That actually go that make up that dimension, right? If you start at the left wheel, you have your tire, how it fits up to the wheel rim itself, which then needs to attach to the hub, which has its own like its own manufactured tolerances and error. And then that hub interfaces with the upright, which also has its own error. And then this like keeps going. It goes through all the A arms onto your tabs. Um, Tabs are generally where you might see actually a lot more error. So this is why we like talk about this here. Reducing error in your tab jigs will like greatly significantly improve the fitment of your parts later. Um, And then obviously you have your chassis in the middle that has its own things. Like a lot of times you might see after welding, the whole chassis might shrink a little bit. So sometimes the width in certain areas is a little off. That shrinkage happens like as like the metal's cooling down, it'll contract a little bit. And then on the left side of the car, it's again the whole suspension assembly. So you might have like 80 different parts between two points that you're making a dimension out of. And if each of these parts is having like 10 thousandths of an inch that are off, this starts to stack up until you might see like in previous years, like we once had, our wheelbase was off by over half of an inch, which is a pretty significant one. Um, like welding tolerances can be pretty bad sometimes where you like actually notice that it's off. Um, I know some people have said Baja like welds their chassis in-house, and sometimes their dimensions might be off like total length. I think sometimes might be up to like an inch, right? Which sometimes like you can accept that, right? But in certain cases, for like a lot of suspension geometry, you might want it to be a bit more accurate. Obviously, since we're using like VR3, which is like professional weld shop, they can get a lot closer tolerances than us, which is really nice when we're doing our design. Theirs is more closer to like 60 thou off for like relative tube placement. Um, but yeah, one way you can really reduce error stack up in your jigs themselves is reducing part count, right? So if I, instead of having a complex assembly where like a million different parts are bolted together, each like on top of each other, I might get a lot more error versus in this A-arm jig, I have one plate that spans between my two sets of tabs. Right, the A-arm is like a solid piece that needs to go into both of these tabs. So fitment's really an issue with if these two sets of tabs are off from one another. So you have to keep in mind like, oh, I have a certain critical dimension here. How do I reduce the part count between any of the components that are in that like critical dimension line? So yeah, you can just count the amount of parts that are between certain tabs or whatnot. Try and reduce that as much as possible. So obviously we have just one connection here, and then you mainly have to worry about like your hole placement and that tolerance there. That's mainly affecting these tabs relative to one another. But then you can keep zooming out and seeing more and more. So I have this corner here, this rear left upper corner A arm, right? Um, its tabs relative to each other has one part, but then to the table itself, this we have this aluminum plate. We have this 3D printed part, which then interfaces with the Build Pro bracket here. So that's already three parts, right? Along with like their bolts and stuff. Which now goes to the table, which is a fourth part. And then I go all the way to the rear right upper A arm, right? If I'm trying to measure like the width, we're seeing everything in that path. On the right side, it's again the same thing. So that's another three components. So even if like my like direct critical like dimensions are pretty good, it's pretty easy to build up a big stack up of error across the entire car. So you do what you can. Generally, I think you can get away with like two parts between any like two critical tabs that are near each other. Generally, I like to use one 3D printed part to either set the plane or whatnot. Like these A-arm tabs are at an angle, so I use this 3D printed part to go from our Build Pro piece, set a different angle, and then I just use an aluminum plate to connect the two. Simplifies it a lot. It's a pretty good strategy for reducing part count. Generally, you can get away with two. Sometimes you might have to do more. Um, but yeah. Um, and also keeping in mind like which manufacturing methods are being used. They'll each have their own varying tolerances. If you ask the makerspace certain printers, you can like look up their general specs of like tolerances versus like our water jet parts, like maybe might be like 10 thou off for overall profile. So yeah, that's all stuff you can take into account when designing these. And then also welding considerations specifically for us. Like welding is a process that produces a lot of heat. So jigs really need to be designed with that in mind. With any project, like you need to design with the environment in mind in which it's being worked. This is where like 3D prints and wood might be like we run into some issues. They're very adaptable. Don't get me wrong, like 3D prints, like you can make like all these wacky shapes. You can adapt to any like tab surface you need, but it does melt or catch on fire. As you can see in this picture here is one of our old front wing tabs um, where the jig caught on fire, it melted, and then you get stuck with all this like burnt residue on your tab. It's not fun to clean off. And also you're inhaling a bunch of fumes, not good for you, right? So, oops. Um, so for safety, we generally say like avoid at all costs putting 3D prints directly on the tabs, right? Like there's a lot of conduction through the actual tab itself. It's being welded to another piece. That entire piece of metal is heating up and it's in direct contact with a 3D print. It's not great. Generally, that's why you see some of the other designs. The clamps will go on the chassis tubes and you'll try and space it as far away as possible without compromising like the stiffness of your jig. Um, but yeah, don't put 3D prints on tabs, please. If I see that, I'll be very sad. So that's why I generally like use a 3D print initially, either off of the Build Pro, like the table materials, or off of a nearby chassis tube, and then connect to either wood or metal. Like wood will burn, but it won't like melt, right? And the fumes are a little less dangerous. So another thing is welding accessibility. If you're not familiar with like the welding process, we use TIG welding, which involves like the use of this little torch right here. You guys can see my mouse, right? Um, and the welders are wearing like these big clunky masks that sort of like that have like a that go dim when a bright light's exposed so they don't blind themselves. Some issues with this is sometimes visibility is like really poor. All right, like they can't see anything in these masks, so it's really hard to tell. If you're having to work around all of these like random pieces that are in the way, just try and think about where a welder might be sitting or standing, like when they're trying to access it. If you have something on the side of the chassis, hopefully they can actually access it from the outside rather than like blocking off that side and then they have to reach around and try and weld on the inside of the chassis. That's no bueno. Or sometimes if you have tabs that are near the bottom of the car, they might be blocked by the table, which means we might have to like take the chassis off or rotate the table if they can't actually access the tab in the weld site. Sometimes that's unavoidable with some of the locations of tabs. Um, but try and reduce it as much as possible. Any unnecessary like visibility problems are a bit of an issue. Um, and also just being able to actually get the torch physically in. So the torch itself like is a pretty clunky piece, and there's a bit of a tip that sticks out. So actually being able to fit that close enough to get like within an eighth inch of the weld site is pretty important, just so they can accurately control their heat flow, and not mess up their welds. Sometimes we run into problems with our tabs that are in double shear, right? Where there's two tabs, especially for a lot of the suspension components because yes, you can access this outside face, but if you're trying to weld both sides of the tab, you might run into an issue where I can't fit the torch in between the two tabs. So sometimes you might have to sacrifice welding on one side of the tab. This can come with some structural concerns and like warping issues where you only have like heat applied to one side, and when it cools, it contracts. So you might see some warping there. Um, we're going to be doing some testing this year to see like how little weld perimeter you actually need. So in any case, if you end up seeing that your tab is going to have like problems getting the full perimeter welded, just see if it's going to be an issue structurally. Um, but yeah, anything else I'm missing? Um, but yeah, try and remember that someone actually does have to weld it. And like you can always talk to one of the welders, Josh or Fauna, are good examples, people you can talk to. Whether or not they think it'll be a problem, like if certain gaps are wide enough. Some things that people forget are bolts and hardware. Hardware can get in the way. Um, Yes, welding considerations for heat. There are some pieces of hardware, like if you guys have ever seen lock nuts, nylock nuts that have that little rubber ring on the outside that sort of like prevent the bolt from coming loose. That will melt and bubble up if it's too close to the weld site. We've seen that happen a lot, so a lot of times just try and use like strictly metal hardware, and also remember that it gets hot when it's welded, so don't touch it. We've done that before too. Um, but yeah, any questions about tab design or tab jig design? I think that's all I have for this slideshow. Um, but yeah. Okay, how do I stop the recording? Oh, it's on this computer.